So that brings us to method 5. Here we wanted to have a method that is more intuitive, that is easier. I don't have to really worry so much about n and also each of the weighting factor. So can I reduce the number of parameters that I need to decide from the manager's standpoint? And the answer is yes. And so in method 5, I introduced to you the exponential smoothing forecast method. Here, this method considers all previous data and gives higher weights to more recent data. So this is the general equation here. The next period demand forecast will be equal to alpha times the current demand plus 1 minus alpha times the last period demand forecast. More formally, this is the equation. I have f sub t plus 1. This is the next period forecast. And this is equal to alpha times the current period's actual demand plus 1 minus alpha times the forecast for the current period. And let's take this to an example. So I leave the equation on the top left hand corner for you to refer to. And let's take a look at this particular example. We want to calculate the forecast for period 2 using the values in period 1. Okay? But we have a problem here. What is the problem? So I have alpha. Alpha I assume to be 0.2. I have the actual demand for period 1, that's 130. But I do not have F1, right? As we can see here. We do not have the forecast for period 1. So how can we start the exponential smoothing method? Well, there are two methods, and I will encourage you to use the first method in this course. So the first method here is I can use the naive forecast for period 2 and then do exponential smoothing for the subsequent periods from 3, 4, 5, 6 onwards. Second, I can choose an initial forecast for period 1 in some manner using expert panel, as we will talk about it in the last segment of this lecture, and then do exponential smoothing for periods 2, 3, 4, 5, 6, and so forth. So let's take the first option in our example in the next slide. So again, I have alpha equal to 2.2 here, and I use the naive method to get my forecast for period 2 based on the actual demand in period 1. I get 130. With that, I can now start to use the exponential smoothing forecast method for period 3 onwards. So what I have here is 0.2 times 155, that is the demand in period 2, plus 1 minus 0.2 times 130. And that is the forecast for period 2. And I get the forecast for period 3 as 135. I use the same approach to work out the values for period 4, 5, 6, and 7. I'll encourage you to pause the video and work through each of these observations. Now, consider the second case in which we obtain the forecast for period 1 in some manner. Say, for example, we can use an expert panel or a manager's experience. And we get 140 here in period 1. Then we can start to apply the exponential smoothing forecast method from period 2, 3, 4, 5 up to 7. Again, we consider alpha equal to 0.2 in this example. So we have 0.2 multiplied by 130, that is the demand in period 1, plus 1 minus 0.2 multiplied by 140, that's the forecast in period 1, and we get 138 as our forecast for period 2. And we can apply the same approach for period 3, for period 4, for period 5, for period 6, and lastly for period 7. At this point, again, I will encourage you to pause the video and work through each of these periods in accordance with the equation to make sure that you understand and are able to calculate each of these values. Now, what if the mean demand level shift at some point in time, how would the forecast model react? Say using a moving average and an exponential smoothing method of different parameters here. Think about it for a moment, and then we will review the two different models with two different parameters for each one of them. Now, as you might imagine, so say we look at the moving average, we have the red line, this is the actual demand, and the green line is the forecast generated by moving average with a window of 2, and the blue line will be the moving average with window of 7. And as you shorten the window, you get more responsive forecast that mimics the demand closer than a longer window. Similarly, for the exponential smoothing, for the green line, this is exponential with alpha equal to 0.9, so this is more responsive to the actual demand as compared to the exponential smoothing with alpha equal to 0.2, right? So this is less responsive to changes in the demand. So these are the observations. MA, where n equal to 2, and exponential with alpha equal to 0.9 are better because they're more responsive to the demand. Well, is this always good? Not necessarily. So say we look at this demand plot here. We have a spike. So this is spurious spike, or perhaps, a spike that happens for some reason that is unexpected. And what happens here is that if you have a very responsive forecasting model, then you're going to get estimates that are not reflective of the stable demand. So let's take a look here, right? So we see that the green line here, this is MA with n equal to 2 and MA with n equal to 7 for the blue line. So the green line becomes a lot more responsive than the blue. So in this case, you don't really want n to be low because it gets too responsive. You want the n to be high so that you average out these spikes that you see in the demand. Similarly, for the exponential smoothing, we get a similar observation here. So in this case, MA with the n equal to 7 and the alpha equal to 0.2 for the exponential smoothing, they are better because they are more stable. They are less responsive to changes in the demand. So based on the last couple of illustrations, it is clear that we have a trade-off here, namely responsiveness versus stability. So if you want your forecast to be able to respond quickly to changes in the demand, then typically in the moving average case, we use a small n, so shorter window, whereas in the exponential smoothing case, we will choose a large alpha so that we place more importance for more recent values. On the other hand, if you want stability, so the ability of the forecast to ignore simple random variations, then we want to choose a large n, so a larger window, so that we can get the averaging effect into our estimate, and that will allow us to smooth or flatten the spikes that we observe in the demand. So that's for the moving average. And for the smoothing case, we want to use a small alpha. Now, what happens when there is a trend? So consider this time series model. We have day on the x-axis and demand on the y-axis. This is for sandwich demand. You can see that there's a upward trend, right? It's pretty conforming to a straight line here. What would happen if we use the moving average method? You see that if you use the moving average method, you will kind of always underestimate the demand. So this is a general problem with the methods that have been introduced to you so far. They are all backward looking. That is, the next period's demand is forecasted by taking all demand realizations and then somehow find a compromise between these values. As a result, none of the method is able to create a forecast that is higher than any of the previously realized demand values for an upward trend, or that is lower than any of the previously realized demand values for downward trend. Right, so this is one example that we see. For an upward trend, it always underestimates the demand. And as you might expect, trends don't only go up, it can go down as well, right? So we have this example here, the US dial-up, broadband, and mobile eras illustrated in this graph. Many of you can see that Netflix and iPhone since around 2008 kind of experience an upward trend consistently, whereas AOL dial-up kind of decreases in number of subscribers ever since 2002, and it just seems to go down